Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, motion of electrons in periodic lattice. That is the Bloch theorem under the paper Solid State Physics. So students, let us see what we are going to learn in this specific module. So what we will do is that we will start with the understanding of the Bloch theorem in one dimension and then go on to the three dimension. We first write down the Schrödinger equation of an electron in a one dimension periodic potential in Fourier space. So you see that it's very important that the Fourier space, the inverse space, is very important in solid state physics. We derive the Bloch theorem from the solution of the Schrödinger equation in Fourier space. The Fourier space is also called the K space. Learn about the concept of what is a crystal momentum. So you see that when we study the motion of electrons in solid, the first thing that comes to our mind is the Sommerfield's free electron theory. What exactly was this? The Sommerfield's free electron theory. Well, actually, the Sommerfield's theory did not take into account the potentials of the ions, that is the potential felt by the electron when it is moving through this solid. So in a sense, these electrons were free. So that's why it is called the Sommerfield's free electron theory. So the Sommerfield's free electron theory, if you take that into account, it was able to explain certain properties of the metal. We could talk about the Ohm's law, for example, conductivity you could explain. But there were many such things which it failed to explain. For example, the positive Hall coefficient, and why some materials are metals while some are insulators. Other important property of electron transport in the presence of magnetic field could not be explained by the free electron theory. Remember, like you see that as soon as you apply a magnetic field, things change. So that is the reason why the Sommerfield's free electron theory could not be understood properly. The things like the Hall coefficients and the effect of magnetic field. Now, in order to rectify the problems associated with the free electron theory, Bloch developed the idea of electrons in periodic potential. See that now the free electron theory, it failed for many experimental phenomena. So naturally, Bloch thought that possibly the electrons are not free, or they are not completely free. So the electron, because you see that it's very obvious that if you remove an electron from a solid, you are left with a positive ion. So naturally, a Coulomb potential has to be there, and this is the periodic potential of the solid, that the electrons at any given moment of time has the tendency to go and jump into this periodic potential because of this Coulomb effect. So naturally, Bloch developed the idea of electrons in periodic potential, and the model is now known as the band theory of solids because of the fact that the periodic potential gives rise to the well-known bands that we observe. In fact, there were many things that this theory could explain, and there are many things that the band theory can actually take care of. So you see that how a simple extension of the Sommerfield's free electron theory to electrons in periodic potential led to the fact that it revolutionized the complete solid state physics. In this model, scattering of electrons is not caused by the lattice but by defects in the lattice. It is very, I mean, like in solids you have many defects. There are many imperfections. It's not perfect periodic lattice. So naturally these defects will sort of scatter these electrons. The one electron time independent Schrödinger equation gives rise to allowed energy states and band gaps. So you see the Schrödinger equation now comes into play. So we can solve the Schrödinger equation for a periodic potential for a single electron, and then we can derive the electron states and the band gaps. This theory is then able to distinguish between metals, insulators and semiconductors. I mean, like, it's a very beautiful theory. I mean, like, how the band theory, I mean, like, you have the bands, and these are bands which are the origin of making a difference to the metals, insulators and semiconductors. And the new concept of effective mass of electron also emerges. Remember, this is again a very important concept, because you see, in free electron theory, the electrons were free to move. So there, at that particular time, the physicists were using the concept of the bare mass of the electron, that is the original mass. But as soon as you have a particle or an electron moving in a periodic potential, then we can no longer use the original mass of the electrons. It has got a certain mass, effective mass, as it moves through the periodic potential, and this mass would be different when the electron is moving from the lowest state to the upper state, or from the upper state to the lower state. Okay, so let us now understand the motion of electrons in periodic lattice and the concept of Bloch theorem. Bloch theorem in one dimension. Let us now try to understand the basic structure of the wave function in one-dimensional periodic potential. The Schrödinger equation for an electron in one-dimension periodic potential is minus h cross square by 2m del square by del x square phi x plus u as a function of x phi x is equal to e phi x. Here ux is periodic with period a. That is, u of x plus a is ux. We now also take into account the phi x to be periodic with periodicity L. That is, phi x plus L is equal to phi x. If the periodic potential was absent, then ux would be 0, and the corresponding solution of the Schrödinger equation would be phi q as a function of x is equal to e raised to power I qx divided by under root of L. So if you recognize this, this is basically like a traveling wave in the absence of any kind of periodic potential. Now if the periodic potential ux is not equal to 0, then the solution would look like phi q as a function of x would be e raised to power I qx into ux divided by under root of n. So you see here that it is now multiplied, this plane wave is multiplied by a function ux. The basic structure of the solution will still remain the same. Note that the wave function phi qx is normalized over the whole system, while ux is normalized over a single unit cell. Also, ux is periodic in A, that is ux plus A is equal to ux, and capital N is equal to L by A is the number of cells in the entire periodic system. So now let us formally derive the Bloch theorem. Now since phi x is periodic, we apply a Fourier theorem and write phi x as a sum of Fourier components. That is, phi x is equal to 1 by root L summation over k prime phi k prime e raised to power I k prime x, where k prime is 2 pi L prime divided by L, where L actually is varying from minus infinity to infinity. Since the potential ux is also periodic, we can then also write ux as a sum of Fourier components as ux is equal to summation over uq e raised to power I qx, where capital Q is the reciprocal lattice vector and q, the reciprocal lattice vector, is equal to 2 pi L by A, where L is an integer. So substituting the results into the Schrödinger equation gives us summation over k prime minus h cross square k prime square divided by 2m e raised to power iota k prime into x phi of k prime plus summation over k prime q e raised to power iota k prime plus q into x phi k prime into uq is equal to e multiplied by the summation over k prime e raised to power I k prime x into phi k prime. So this is the Schrödinger equation by substituting the results that we had got. This is a very nice figure, and as you can see from here, this basically tells you about what exactly is a block function. So block function is a wave. The smooth curve represents the wave e raised to power I k dot x, which is modulated by the atomic live wave functions ux. So we have got now two waves here, one which is the wave traveling wave e raised to power ikx, and the other is the atomic wave function ux. Now what we do is that this Schrödinger equation which we have written down in the Fourier space, we multiply it by e raised to power minus iota kx by L, where k is equal to 2 pi L small l divided by capital N, and we integrate it from 0 to capital L. So this gives us h cross square k square divided by 2m phi k plus summation over k prime q delta k prime comma k minus capital Q phi k prime into uq, which is equal to e into phi k. In deriving these previous results, we have made use of the following results. It is 1 by L integrating from 0 to L dx e raised to power iota k minus k prime minus kx gives you delta of k prime, and 1 by L and integration of from 0 to L dx e raised to power iota k prime plus q minus k into x gives you the delta function, that is delta of k prime comma k minus q. So now we can rewrite this equation, the Schrödinger equation, taking into account that h cross k square by 2m is equal to, in a short form, that is e k naught, and k prime is equal to k minus q. So the expression then becomes the Schrödinger equation e k naught minus e multiplied by phi k plus summation over capital Q phi k minus q into eq is equal to 0. So this is a Schrödinger equation in Fourier space. Non-zero values of the solution exist only at discrete and uniformly spaced values. Let us consider a solution for which phi q is not equal to 0 for at least one q equal to 2 pi m by capital N. Now from the previous Schrödinger equation in Fourier space, let us choose one component, that is phi q minus capital Q prime, that is k equal to small q minus capital Q prime. Then this Schrödinger equation in Fourier space then becomes eq minus capital Q prime naught minus e phi of q minus capital Q prime plus summation over capital Q phi of q minus capital Q prime minus capital Q into uq is equal to 0. Now set capital Q as capital Q minus capital Q prime. Consequently, this Schrödinger equation in Fourier space becomes e small q minus capital Q prime naught minus e into phi of q minus capital Q prime plus summation over capital Q phi small q minus capital Q into u q minus q prime is equal to 0. So as you can see that this equation is different from the previous Schrödinger equations in Fourier space, but involves the same components which are discrete. This shows that the Schrödinger equation is a collection of algebraic equations for a set of wave functions components, and all other components are 0. The various phi k's are connected only if they differ by reciprocal lattice vectors. The solution of this equation, that is the Schrödinger equation in Fourier space, can be written in the form as phi k is equal to summation over q delta k comma small q plus capital Q into uq. Hence, a non-zero solution exists if k is equal to small q plus capital Q, that is k and q are connected by a reciprocal lattice vector capital Q. So now the corresponding real space solution is phi x is equal to 1 by root L summation over k prime capital Q delta k prime comma k minus capital Q u capital Q e raised to power I k prime x is equal to 1 by root L summation over uq e raised to power I small q plus capital Q into x. Therefore, phi of x is equal to e raised to power iqx into ux divided by root n, where ux is equal to 1 by root of a summation over capital Q uq e raised to power I capital Q into x. This is nothing but the Bloch's theorem. When an electron moves in a periodic potential, the solution consists of a plane wave e raised to power iqx modulated by a periodic function ux, which has the same periodicity as the lattice potential. It is usually customary to write the non-zero value of phi x by phi qx for same q. Q is the Fourier component for which the solution is non-zero. So now let us see that phi q at x plus a, what it becomes. So you add a to x. So this implies on the right hand side we have e raised to power iqx into e raised to power iqa uk function of x plus a divided by root of n, which is equal to e raised to power iqx uk x divided by root of n, which is basically get back phi qx. The Fourier component q is called the wave number and h cross q is called the crystal momentum. So you see here that the wave function is periodically repeated and the periodicity is a. Now if we choose q, then it satisfies k is equal to small q plus capital Q, that is small q and k, they differ by a reciprocal lattice vector, and from this phi q can be constructed. If we choose small q plus capital Q prime, then it satisfies small k is equal to small q plus capital Q prime plus capital Q, which is the same set since both the sets differ by the reciprocal lattice vector capital Q. This means that the two wave numbers are distinct only if they do not differ by any reciprocal lattice vector. We then have to choose small q from q is equal to 2 pi m by capital L, where q lies between minus pi by 2a to pi by 2a, that is, it lies within the first Brillouin zone. Now we generalize our results to Bloch theorem in 3 dimension. We now extend the Bloch's theorem studied in the previous sections to 3 dimension. We now generalize our study to a box of volume V, which is equal to L cube, in which the wave function of the electron phi r is periodic according to the following. That is, its periodicity is in the x direction, it is in the y direction as well as in the z direction. So what we do now is that we express this wave function in terms of the Fourier components. That is, phi r is written as equal to 1 by root of v. Now compare this. Now earlier we had written 1 by root of L, but now it is 3 dimension, so we say it is 1 by root of v summation over k phi k e raised to power I k dot r, and the potential u as a function of r is equal to summation over capital Q, that is summation over the reciprocal lattice vectors e raised to power capital Q dot r into uq. So both of these are now in terms of Fourier components. Note that if e raised to power I k dot r plus L is equal to e raised to power I k dot r, this vector, this is a lattice translational vector, that is this t, and then small k is equal to capital Q. This collection of such vectors is called the reciprocal lattice. So proceeding as in 1 dimension, we generalize the Schrödinger equation in the Fourier space to 3 dimension as ek0 minus ek phi k plus summation over the reciprocal lattice vectors capital Q u q to phi k minus q is equal to 0. Thus, we get a very similar result. That is phi q as a function of r is equal to e raised to power iota q dot r u q r divided by root n. So this is a generalized Schrödinger equation in Fourier space in 3 dimension. Now here, if you take the capital N is equal to V divided by capital omega, where capital omega is the volume of unit cell, equals the number of points in the lattice. Also, uq r plus t is equal to uqr is a periodic function with periodicity the vector t. There are infinite number of solutions phi qr for each q. Here q is called the block wave vector. The many solutions for each q are distinguished by the band index n. So we write phi qn as a function of r is equal to e raised to power iota q dot r into u qn function of r divided by root n, together with the corresponding band energy enq found from the Schrödinger equation. So students, let us summarize what we have learned in this module. In this module, you have studied about why the block theory was developed in order to rectify the problems of the Sommerfield's theory. So again, Sommerfield's theory was dealing with the free electron case, but the block theory deals with an electron moving in a periodic potential. So it is no longer free. It's a nearly free electron. Okay. Then about the concept of electrons' motion in periodic lattice via the Bloch theorem in both one-dimensional and three-dimensional. It is simple extension of 1D to the 3D effect. That is what we have discussed. And this Bloch theorem, what is the Bloch theorem? It is to do with the periodicity of the wave function. Everything is now periodic because the potential is taken to be periodic. And then about the expressions for the wave functions in Fourier space. So we had solved it completely in Fourier space, not in real space, the K space. And then about the concept of crystal momentum, which is very important. Crystal momentum plays a very important role in also trying to understand the effective mass. About the Bloch wave vector, for which each value of the wave vector q signifies infinite number of solutions which are distinguished by the band index n. So for a given value of q, when you have more than one solutions, these more than one solutions are basically the different bands and they are given the index n. So you have q and n. So for each q you have many n's, and going from like different band structures we have. Thanks for visiting ePathshala.